Geospatial Web Working Group. We've got a couple of kind of community intro lightning talks. We've got first up Mike Brockman from the Open Geospatial Consortium. We've got Jimo Sarodio from Sylvia and Reforestation, and we've got Bill Thorpe from StoreJ. Then we've got our featured guest speaker, Dr. Majid Hojati, and plenty of time for kind of Q&A discussion. One particular kind of agenda item that I wanted to throw out there, and we'll kind of dovetail with Micah's presentation, is the idea of kind of taking this group and rolling it into an Open Geospatial Consortium working group. So I'll kind of leave it to him to talk a little bit about what that is and what they do and why that could be kind of a cool home for this working group and what we would all be able to bring to that table or benefit from them as well. So that's all I'll say for now. And then I'll pass the microphone over to Micah.
Awesome. Thanks so much, Taylor. Really appreciate the intro. Great to see everybody again. I've been to one of these meetings so far, hoping to come to many, many more, especially if you all decide to kind of roll this group under the umbrella of the OGC. So let me go ahead and share my screen. Just got a couple slides to talk to. I won't be too long today at all. So let me go and find this talk really quick. Got a question actually before I even start with the slides. How many of you have heard of the OGC before? Raise of hands. All right, so looking about half, few people who are, I'm getting thumbs up who aren't on camera. How many of you are part of an organization that's an OGC member? Anybody now? Anybody aware of that? Oh, Taylor, we know you are. You don't have to raise your hand.
Me? Okay.
How many of you have a sense of what the OGC does? Anybody want to give me a bumper sticker for what the OGC does? Go ahead and jump on. I won't call on anybody. Just jump in and tell me what the OGC does real quick.
Well, since I'm the only one who belongs to the institution, which is actually wrong, because we've got John and Matthew on here and Thomason, and they're all working with me. So if my organization is, then so is theirs. But my understanding is that they kind of provide a vehicle to propose and adopt standards for interoperability.
Love it. That is a great overview. And that certainly encompasses some of what we do. But to be honest with you, the OGC is a lot more than standards. So you guys are all seeing my slides, right? Perfect. Got those pulled up. I'm just going to do a really quick 5-minute introduction to OGC and also to Taylor's earlier point, talk about why it might be mutually beneficial to bring this working group under the umbrella of the OGC. So let's start with a really simple example. I've got my Apple map pulled up. I'm looking for a lovely park right near my house in beautiful Santa Barbara, California. And I like this park a lot. It's got disc golf course, super, super nice. I click on a point on the map and here we go, Evergreen Acres Park, right? So I've got my place name. I can kind of see the boundaries of where this park is. And of course I can share it with a friend if I want to. Then I go on a Google map. Looks like the same park, different place name. I kind of see a different boundary for this park, right? And of course, if I were to share this with a friend and they were using Apple Maps on their phone, it would be a Google Maps link, right? So place names, boundaries, and location sharing across these two different, very commonly used mapping platforms are not interoperable, right? So what we do at the OGC is we drive interoperability because interoperability makes maps work for everyone. So what is the OGC? Really quick overview. First of all, we're innovation. So we have an innovation program, and through this program, we have over $2 million in annual sponsor funding. Basically, our big government sponsors, NASA, NGA, US Army, give the OGC money, which is then distributed to our members to help them solve hard problems. So our members have funding available through our sponsors. One of the problems we're working on right now is how can we build GPS for the moon? It's a really tough problem to solve, but one that we're actively working on with some funding from NGA. We also do standards, as Taylor mentioned, right? So we write these long technical documents that set the standard for how to use geospatial data. And we have more than almost 2 million operational data sets using OGC standards, right? So these are the data sets that we know about that are fully operational. There's a lot of implementations of OGC standards out there, even outside of these operational data sets. And one good example of one of our standards, in fact, one of our oldest standards, is Web Map Service, which some of you have probably heard of. This made internet maps work, full stop, right? Before this, there were proprietary solutions for sharing map data. Web Map Service essentially made maps work on the internet. And then we're also a community. So we're the oldest and largest nonprofit community of geospatial technology experts. We've got 500 members from academia, government, and private industry, pretty much evenly distributed across those domain areas. So our mission is to make geospatial data fair. That's findable, accessible, interoperable, and reusable. So my question for you today is, does the Decentralized Geospatial Web Working Group want to work with the OGC? This is my central question to you all, and something that Taylor will certainly follow up with all of you. And here's my proposal, right? So first of all, you've already got a working group. OGC has domain working groups. These are groups that are completely open to the public. Some of our working groups are only open to OGC members. Domain working groups completely wide open. And this group could become an official OGC domain working group if the members of this group decided they wanted to go that route. In terms of the leadership of this proposed group, since the University of Maryland is an OGC member, Taylor could be elected the chair of this new domain working group. Now, one of the cool things about the OGC is that we vote on everything, right? So me as OGC staff, I just can't come in and say, hey, Taylor's the new chair of this group. We'd have to have an election, right? But it's kind of one of the fun processes that we go through, and really, I would say, emblematic of how the OGC works, right? It's a community. So under this new proposed domain working group, the chair plus a charter document would determine what the domain working group does. So our working groups are very much member driven. And of course, the benefits of coming under the umbrella of the OGC would be broader exposure to the geospatial technology community for this group. And with that, expanded networking and funding opportunities. So Taylor had some questions for me. How often does an OGC working group typically meet? Another question was, what kind of business is done and what are the workflows? And thankfully, there's a single answer. OGC domain working groups are member driven, right? So that can all be dictated by the members of this group in terms of what you want to talk about, when you want to meet, and what you actually want to do. So that's a really cool thing. I would say there are some downsides, right? In that structure can be helpful. And that's where, if you want to learn more about the OGC official processes and really get involved with those, both in terms of writing standards and getting involved with their innovation program, that's where somebody like me comes in to help guide you through that process. So let's go back to this first very simple example that I threw out there at the beginning of the talk, right? Google and Apple are both OGC members. So if they wanted to solve these problems, they could, right? It's entirely within the realm of possibility solving an interoperability problem like this between two huge companies. They haven't made really an effort in that front so far. I think it makes sense from a business perspective why they don't, but they could, and the OGC provides the platform to solve problems like this. So OGC provides the opportunity, members take the initiative. That's basically how we work. So that's all that I wanted to share with you today. Happy to follow up with any of you individually if you want to talk about the OGC more, just learn more about what we do. Got my contact info on the slide. Happy to paste my email address into the chat as well. And certainly plan on having some more discussions with Taylor about if and how we want to make this collaborative relationship work. So thanks a lot. Not sure if I have time for questions or not, Taylor, if there's questions out there.
So I want to make sure we've got time for all the presentations. So what we'll do is hold it to the end, and then we can kind of usually have some open discussion at the end, and we can bring that back around and definitely have some discussion if there's questions about it.
Sounds perfect. Thanks a lot.
All right. So next up, we've got Jimo Serodio. Let me know if I'm saying that incorrectly, with Sylvie and reforestation.
Yeah, Jimo Serodio, but Jimo, I usually get that wrong. So yeah, hey everybody. It's great to be here. Can I share my screen for a couple minutes as well?
Yeah.
Thank you. It does show host.
Made you co-host, so you should be able to.
I think now it will work. Yeah. Okay, so I'll keep this short. Basically, this is an invitation to collaborate. I'm personally not super technical. I do lead a team, and we've had some grants and specifically an initiative with Filecoin that I thought was worth sharing. So at a very high level, I'm building Sylvie, which is a reforestation protocol. Let me open this slide real quick. Basically, we look at the tree from an asset class perspective, right? So this asset class comes with various milestones that need to be met for reforestation to happen, and each of those milestones is ultimately verifiable on the ground. This is just a generic timeline because we really have 40, 50,000 plus unique tree species. So what we're building is also sort of species and location specific methodologies. This is very short time that I have here, so I'm gonna try and be very quick. But we basically evolved from like a version 1 of the app where we were registering assets on the ground with an extensive form. In this case, it's like a demo proof of potted sapling. But we have focused quite a little bit on propagation. So our current version deployed is a little bit more extensive, where our claims are really very custom claims depending on what the claim event calls for. In this case, it's demoing an environment registration for a potted bed. And so you can see here a proof of, I guess, 12 potted beds, and we have a recipe for how to create those claims. And the form is tailored to that as well. And then ultimately, that information is stored. We store it on IPFS, but we do have these info cards that keep sort of all the historical data and metadata for that. And then we do have basically an accounting system for batch accounting. When you're creating claims for multiple assets at the same time, we need to scale that indefinitely. So we have an accounting system. It's also Web 2 and Web 3. And ultimately, you can customize these methodologies according to pay, which is dependent on labor markets, and the species, which is more like the allometric model of the trees. So with that said, what we're now building towards is how to start geofencing this, how to register these assets, and also strive to be interoperable with this data. And the last point I will make, oh, and by the way, so we've piloted in rural and urban settings in Kenya. We have a decent project that is sort of grant funded. We're working with farmers. We've worked with 30 farmers, and they basically we're focusing on propagation at the time, but a lot of reforestation is also about to happen. And we've worked with over 100,000 trees that we've propagated in-house via the protocol. But what I'm here to talk today is, so in the Boston Sustainable Blockchain Summit Hackathon, we actually won first place for a concept called Open Trees, where the Sylvie protocol was building interoperability framework for other projects to kind of ingest data and update the model. So if you're not familiar with CO2.storage, it's basically sort of a natural capital storage solution for things like carbon credits, et cetera. And we were working on Open Trees as a specific focus, where Sylvie can produce a lot of the MRV, but then other protocols like FarmOS can then interop with that data in a similar way to how the previous example with maps was discussed. And the invitation to work on is, we've defined like a tree model, an open tree model for structured tree data. But we basically are coming up at a point where we want to be able to use our methodology data specifically. You can see this later, but I want to keep this presentation short to respect everyone's time. But basically, let me stop sharing the, oh, there you go. So basically we intend Open Trees to be as open source as possible. Sylvie itself is working on a few methodologies that are more logistics oriented, the claims profiles, the sort of claim recipes. We also trigger automated payments for settled claims. We are building on Cello, so we've also received a couple Cello grants. But ultimately, there's all sorts of methodologies and a vision for open tree data in this vision to have 1 trillion trees globally. So this is like, an open, friendly, call for collaboration, for guidance, for anything that is out there. We're already collaborating across a few projects, but if anyone's interested in trees or reforestation or this sort of geo querying approach to tree data or natural capital data, I would love to chat with you, and I'd love to collaborate. Thank you.
Awesome. Thank you, Gmo. I know that there are some other folks on the call who are certainly interested. So we'll save to the end for any kind of comments or discussion. And then we've got up next, we've got Bill Thorpe from Storage.
Thank you. All right. Let's see if I did that correctly. No, it shared that screen. All right, I'll move it over here. Can you all see my screen?
Yep.
All right. So for this audience, I'll just start off with storage is not a blockchain. We have a utility token that operates on the Ethereum blockchain. We use that for financial transactions in our network. But the nice part there is that it's all US dollar equivalents, and there's no kind of weird tokenomics that we have to worry about. So back to what are we? Storage is a globally distributed object storage service. So think S3. And I am kind of near and dear to the GIS crowd because I've worked in GIS for 15 years, and I had so many problems with files at the end of the day. It was more about the file system that kind of slowed me down. And so I went from working in GIS to working with storage, and 25,000 points of presence backing up our network. So we're not making 25,000 copies of your data. And forgive me, I made all of these slides very tongue-in-cheek. We use a process called erasure encoding. It's the same thing that happens in RAID hard drives. It's math. You split a file into N pieces, but you only need K pieces to put that file back together. So in our case, we break a file into 110 pieces. Only 29 of those pieces will be necessary to put a file back together. We'll get to why this is all important. This is kind of this neat sort of like super RAID concept that we've got. We upload those to the storage network. There's 25,000 storage nodes. We're uploading to 110 of them, but we've created kind of a market ecosystem, the fastest 80 win that. When we download, we should have up to 80 copies of it still on the network. And we're downloading 29 of those pieces. So of the original 110, we now only need 29 here to reconstitute the file. We've got a race again. We've got market economics happening where the fastest nodes are the ones who are going to be delivering your data. They're the ones who are going to get paid. So that's how we go from this map of 25,000 dots to you actually storing and retrieving your data. The great part about having a globally distributed network is we don't care about the speed of light, right? If you were storing your data on Amazon or something, you'd have to worry about, well, which data center do I put it in? What region do I put it in? We're kind of globally consistent in the speed that you get your data. So you can upload your data in New York, go download it in Tokyo. It's basically the same speed. So that's a really cool feature of the storage network, is not only are we faster for large files than the S3s and Google Clouds of the world, but we're faster everywhere. So you don't end up making all those copies, right? And RAID 1 should be embarrassing, right? We don't want to make full copies of our data. How would you use it? Well, we are trying to compete against the S3s of the world. So the best way to compete is to steal what they're already doing. There's so many things that work with S3, like GDAL. In the GIS world, lots of tools are built on top of GDAL. So you should be able to just point to an HTTP website, right? So if you use curl, or if you use any sort of remote file system browser tools like CyberDuck, you can use it with this S3 compatibility layer. You can create a local file system mount if you're just more comfortable with like dragging and dropping the files locally. You can also point BitTorrent at HTTP endpoints. So if anybody's curious, I can teach them how to do that. But so you can go from having distributed storage to also, if you think the community wants to be involved, you can just host a BitTorrent link and then additionally get some kind of like free downloads by the community kind of helping out. We have IPFS endpoints too. You could also do everything natively, avoid kind of our hosted services, use our Go bindings or custom language bindings, use our CLI tools. Our clone is a really popular tool that has native integration of the storage network. The only thing when you do natively and you're uploading, remember you're uploading 80 pieces out of 29. So your uploads are going to be about 3 times slower than using our nice S3 services. Storing data is not actually hard. It's making it available and durable and secure. So we've tried to go much beyond like some of the other, like we store data, like blockchain kind of concepts to be like, no, it's like kind of the enterprise SLAs here that are worthwhile and useful. But we also have a pricing that's basically like 1/10 the cost of Amazon or Google. So really affordable, really green. We've surveyed people. It's hard to really pin this down, but we believe that 80% of our network is running on existing hardware, right? So nobody bought hard drives to make this work. These were under provisioned devices that were already out there, right? We didn't pour concrete, build giant data centers. So we believe that we're kind of like 90% greener than a lot of the solutions out there. Really good for hybrid cloud, really good for large files, high throughput, really good for global availability, really good for being simple, right? You don't want to like manage all like your tiers of storage. If you ever paid attention to the S3 ecosystem, there's like, oh, well, I'm not going to use this very much, but I'm going to use this more. Well, we're like the price of the cheap storage, but we're actually always online. So I've gone through this super duper quick, but the kind of high level is like, we've got a really good distributed storage that's really kind of predictable and much, much, much cheaper than the major companies out there. And you should write down my email address and let me know if you're interested in trying to use it with GIS, because I haven't found anybody actually using it with GIS yet. So I would be excited to see how it works.
Awesome. Thanks, Bill. All right, so we'll save questions till the end, and that brings us to the kind of featured guest speaker. We've got Dr. Majid Hojati. I think he's still with us, right? There he is. All right, Majid, whenever you're ready.
Yeah, thanks, Taylor. Okay, so does everyone see my screen?
Yep.
Okay, so my name is Majid Hojati. I'm gonna talk about distributed spatial data sharing, a new era in sharing the spatial data. This presentation is part of my PhD work that I recently defended, and I work under supervision of Stephen Roberts, Dr. Colin Robertson, my company, Rob Fike, and Dr. Carson Farmer, which is part of this group as well. So to get started, I'm gonna quickly go over the outline of my today's presentation. I will go through the introduction, and I will discuss about what's distributed spatial data sharing, how we define it, and then I will discuss some of the areas that there was gaps when we wanted to share spatial data on the network, like for example, running a spatial temporal queries, or addressing concerns of geoprivacy when we want to share data on distributed network. And at the end, I will go through a recap about what we know and the conclusion and future works. So we all know that spatial data sharing behaviors are changing. Over the past decade, we have a lot of VDI platforms that appeared, and they allowed the users and individuals to contribute in data collection and data providing. We have easy access to IoT sensors, devices, and each device is collecting geographical information and other type of parameters over the time, and people are using these sensors to share their information with those platforms, with social media, VTI platform, and other existing devices. We are in a kind of big data evolution, and the entire evolution happened from moving from centralized SDIs, which were government enterprise were in charge of data collection and data sharing, special data collection and sharing, to more individual and user centric. That this evolution is happening through the introduction of Web 1, Web 2, and Web 3 these days that we are all familiar with. So this data sharing revolution is happening and it is in different scales. So also, when this change is happening, the role of individuals is increasing in data sharing environment. And with this increase, there would other gaps appear and shows themselves very well. Like, imagine that the user is contributing in a VGI platform or in a other platform, and they are sharing their location information. The concerns about ownership and who owns those data that they are sharing appears there. Or if, for example, you want to contribute in a platform, you have to agree with their term of services and those related policies that they exist there. And if you are, let's say you are from an indigenous community, for example, that the policies that you have to agree in terms of services doesn't align with your concerns, you can't use that platform, and it prohibits your access and accessibility of those platforms for certain groups. And also we have a lack of transparency and limited control of the contributed data and data that we as individual and users are sharing. So the whole change and these concerns lead to a kind of power imbalance in data economy. If you look at the chart in the right side, we have a kind of see an increased number of research about data ownership and concerns related to data ownership over the past few years. We have this social change happening, and it's also social technological change that is happening. And we also have the distributed systems, which we all know about it. We have different levels of distribution, can be like in a file level system like IPFS that we have in decentralized application, or in process level, which we know that we also see the huge increase in number of research that and R&D that is happening in this area. So now that we know, we see that currently the change, socio-technological changes happening, individuals are contributing more, and those gaps are appearing. We also have distributed systems that gives us ability to communicate between node peer-to-peer connection and sharing information through the peer-to-peer networks. So the gap of ownership and control might be solved with utilizing this new distributed system technology. And this is the area that I started to work and wanted to see how we can address these gaps and solve some of the existing user-centric problems, data sharing problems using distributed systems. So if we want to get a bit deeper into the concept, we need to know what is spatial data sharing. If we look at the spatial data sharing, we can break it down into four main components, from technical part of that, which is data models, data structures, and standards that already exist there for centralized systems. And as we know that OGC is playing a big role in defining those standards. We also have policies and legal aspects of the data sharing, like access, privacy, copyright, and related concerns. We have social concepts and semantic of the data that is being shared over the different devices and networks. We need to acknowledge that each of these components we can break it down to the smaller subcomponents. But if we want to study the spatial data sharing environment, we cannot study one single component. We need to see the holistic part of that. And we can, for example, focus on the technical aspect of that. We need to address the policies. We need to address social concerns of the usability of those technology and standards, and also semantics of those areas. So this is the part that we have to keep in mind when we are studying this area. So my research was focused in two main socio-technological aspects. First, I wanted to try to identify the new era of spatial data sharing as a distributed data sharing and find out the characteristics of this environment. What is about this environment that make it separate from centralized and user-centric era. And I also wanted to look at the technical aspects of the, let's say, use of this. We want to use distributed systems to share geographical information. We should be able to, for example, query and process spatio-temporal queries on this system. What approaches we can take to address it, and also what approaches we can take to address geo-privacy and control concerns when data are being shared on this system. And at the end, the last part of my work was about looking at socio-technological consideration for using distributed spatial data sharing in a community level and indigenous level data sharing, which I don't get into that in this presentation, and mostly I focus on part 1, 2, 3. So as a first part, what is distributed data sharing era and how I define it? So as I said, when we want to look at this spatial data sharing, we see 3 main role players in a spatial data sharing. We have data producers, data controllers, and data users. These roles exist there, and over different eras, different players play that role. For example, we have central spatial data sharing, which was earlier type of data sharing that SDIs were more highly controlled by the government. Government had the funding and sensor and all of those devices to collect spatial data. Over the time, the role of users increase, the sensors get more accessible, users start to collect data and share with the platform. So it becomes user-centric. And that user-centric has transparency, ownership, and control challenges. The next era is the distributed spatial data sharing, which we want to address transparency, ownership, and control challenges that exist in user-centric data sharing environment. To address these challenges, we define distributed spatial data sharing, which individuals and communities are active in all dimensions of data sharing. They can be control, producer, controller, and the user. In a user-centric environment, data controller is the platform. You as user contribute to the platform, and you have certain rights depending on a jurisdiction and for the area that you live, but the platform, you agree with the term of services of the platform. So you are not, as an individual, you are not controller. But in the new era, you as an individual should be able to decide where, when, and for how long your data is accessible to the platform or other entities. As you see in this chart, in the right side, the left column is the data producer, middle one is controller, and the right side is data user. The connection between data controller and user gets more complicated because individuals are in charge of the data that is being shared, and the access between for a piece of data that they are sharing gets granted by individual or platforms that are responsible for that part. So there is gaps in distributed spatial data sharing query processing on a spatial temporal data is one of the gaps. Geoprivacy is there, which is not clear how we can address it. Access control methods on distributed networks, which is a question mark there, and geo-enable smart contracts is something that exists there. We have social gaps there, which is concerns around the acceptability of distributed spatial data sharing in the different communities, different scales, role of distributed spatial data sharing, licensing and ownership of the data, and how it plays as a tool for advocating transparency of the data sharing environment. In my work, I focus on those highlighted one: query processing, geoprivacy, and social concepts. So for the query processing part, I propose DS3, which is a kind of distributed spatio-temporal tree. So how we know that as an infrastructure of a distributed system, we have peer-to-peer networks, and those query processing of peer-to-peer networks are complicated. We have for spatial temporal data, we can have overlap between a spatial object. We don't want to scatter spatial data, and we have complexity of the queries themselves existent. We have different type approaches to address multidimensional data query processing, like multi-dimension to one dimension, like Z-curve, or using indices methods like H3 and similar indexing methods to convert two-dimensional data or three-dimensional to one-dimensional. We can use multiple DH3s in some research, and also there is approach to construct a traditional index structure and keep that index structure up to date using the nodes. Nodes are responsible to keep that index structure up to date. So this approach is the one that is at the backbone of DS3. So here is just a summary about abstraction of the data from geographical object to the data model that we use, data model to the tree structure, which can be R3, quad-tree, and all of those existing tree structure. And in the some of the approaches for peer-to-peer network data sharing, there was super nodes that are responsible to keep that tree structure up to date for the network. In our approach, each node is responsible to keep that version up to date, and whenever one node is contributing to the data, they update that chain on the blockchain, and the latest version of the tree structure, that tree structure is lives on a blockchain chain at the lives on a chain. So, however, how this tree structure is able to address a spatial temporal query. So we have a spatial topologies that we want to address. So we can use a quad tree or any type of tree structure that addresses some of the spatial topologies. We have temporal topology as well. We see each geographical event, geographical object, as a timeline that has a timeline, and it's lifetime of that geographical object. It has a start, end, and the duration. So when we have this structure of the time, we can define temporal topologies like equals, meets, overlap, during, starts, finish, and proceeds. So we have temporal topologies, spatial topologies, and we want to query our data using these two criteria. So for spatial topology, we use a quad tree. For temporal topology, we use interval tree. We combine them and create a two-level tree. The top part of that tree is an interval tree. The bottom part is a quad tree. And then we store it on a IPFS. We add some metadata to standardize it. We need to define a conflict strategy, how we can update it in terms of conflict, and we are good to go. So this is one example of the DS3 structure. As you see, it is a two-level tree structure. We have an interval tree at the top part of that and a quad tree at the bottom part of that. The interval tree has a temporal level that user, when we create that data set, that index, we set that interval level, temporal level. And interval tree is a two branch tree. So it has left, right. So we assign 0 and 1 to that. And quad tree, it's 4 branch tree, so we have a quad index there. So if we combine these three, each leaf of the tree structure can give us an index that we call it DS3 index, which is the root of the tree / temporal index 0, 1, 1, 0, depending on how deep that tree goes, and the spatial index, which is our quad index. So we see it as a folder structure, and we store data under this tree structure. And because it is similar to a tag graph, we are able to store it on IPFS easily and query using this folder structure from IPFS. The reason that we are using quad tree is that quad tree is a kind of uniform, it has uniform structure. It's clear that there is, for example, always 4 items on each branch, each node. And later we are able to exchange this quad tree with more advanced hierarchical data structure like discrete global grid systems, DGGS structures, H3, or other existing multi-resolutional hierarchical data structures. So we have this structure here, so we can have different query processing approaches. It's able to address queries that include the time. If it's only the time component in our query, we just check the top part of the tree structure, and based on that, we retrieve all of the data in the temporal part. If it is in a spatial part, if it is a spatial part, we just check all of the nodes and all of the branches of the inner tree and go to the part of which is the bottom part of the tree, which is spatial, and we query them. Or if it is a combination of spatial and temporal parameters, we query the top part of the tree and then query the bottom part of that tree. We need to have a kind of a exact match check for true negative concepts, which is we also need to check them, but it increase the query performance. So we did a performance comparison with the existing tree structure. We used we used the DS3, interval tree, quad tree, and one arc tree, which in the arc tree we consider the third dimension of the arc tree as a time, and we perform different queries on the data set, and our tree structure does relatively a better performance compared to the existing models. However, it is for a small to medium to average size data sets. So DS3 has its pros and cons. It supports vector data. For the raster data, we have to come up with converting those vector data to models like dGGS, which each pixel has its own ID, and we are able to construct that hierarchical structure there. We don't support temporal queries, extend queries for the raster or multi-resolution aggregation of the data. And for the thing, we don't extend support extend queries. Performance-wise, it does a good performance on a small average size data sets, and it is optimized for time series data, which like sensor data that they are collected over the time, and we don't need to update the entire tree structure over the time, because we only need to update the top part of that interval tree and construct that. So it helps us to retain the main portion of the tree untouched, and if we want to update it, we update the top part of that tree structure. We increase the performance of the updates. It's not optimized for deletion of the data, because when we delete an item from the original structure, it needs to reconfigure interval tree, and it has a huge impact on the restructuring of the tree. So it's not optimized for deletion of the data, and it only supports the special topologies that underlying a special index supports. Like if you are using quad tree, it supports certain special topologies. So the next, now that we have structure and we know how to share and query data on a distributed system, we need to have approaches to address geoprivacy. If you as a user, you want to share a point on the network, how do you want to add geoprivacy in the spatial data that you are sharing? So we look at the social spatial network data, and in this network data, users don't want their location being shared, saved, or inferred for different purposes like advertisement. Majority of the users don't have a transparent access to the data flow from the operation system to the application and to the server. They don't know what data is being transferred through this entire system for when they are using social network data. And there isn't any way to have a fine-grained control over data that you are sharing with those networks. You have to share exact location. So if we look at the existing geoprivacy models, also we have the dummy location, jittering location, space transformation, and space clubbing, and there are other groups as well. However, all of these models that exist, they need a centralized entity to have data. We send data there, that central entity transform or data, or for example, if it wants to use space transformation, transfers the entire data into another system and returns that. So we need to share our data with that entity, and that entity applies geoprivacy model on that. So we don't want to do that. The user shouldn't force to share their location with the entity, third-party entity, and to get, for example, a level of geoprivacy there. So we define a kind of framework for decentralized geoprivacy, that in this framework, users should be able to preserve local control and sharing the location without the need of any central entity. User need to retain their autonomy to define, for example, the resolution of data that they are sharing with the third party or other users, and that resolution can be determined like with the factors like trust that user has with the nodes in their network or nodes in the social spatial network. And having this variable, because it should be fine-grained, it changed based on the trust. So we need to have a data model that allows us to share data, spatial data, in different resolutions, which in our case we use discrete global grid system data. That I can explain about it if you need at the end of this presentation, but discrete global grid system allows us to have a kind of multi-dimensional hierarchical structure of the data. So we propose a k-anonymity model, which is based on this DGGS, and it's the way that it works, each user has a minimum K and maximum K. So they have minimum K is for the data that they want to share with the nodes or other users that have the highest level of trust. And maximum K is the one that you share with the people that you don't trust or don't know who are they, or you have a low level of the trust. So each user is able to share their location as an area, not as a point. So there is a uncertainty level in the location that you share. So you can share it with a smaller hexagon level if you are using, for example, a hexagonal discrete global gauge system, or higher, bigger hexagon level. So once a user wants to share their data in a distributed peer-to-peer network, they first get the location of peers around them, and each peer is sending their location in a different resolution depending on their setting. And or node that wants to share their location applies k-anonymity under those data that receives, and per each k, they assign a certain resolution. And depending on the trust level that exists between nodes, they share that certain cell with a certain diameter. And it applies to the, when you want to share point, or for the line data, you can break it into the multiple cells and apply it on multiple each cell separately. So this approach also has a pros and cons. It is we use the discrete global grid system for k-anonymity model, and we also as network infrastructure is peer-to-peer network. So DGGS allows us to have an explicit level of uncertainty in shared location data. It allows us to have a parent and child relationship there, and our approach embeds the minimum area which is required for the k-anonymity models, centralized k-anonymity models, and users store their data, their location data on their own. They don't need to share it with the central entity, which is the main goal that we wanted to follow. And there is cons as well there, which is it is a k-anonymity based model, so it has limitation of the k-anonymity model, and it is limited to the number of online users. It's not easy to integrate it with the existing social network. So as a conclusion, we know that we are at the edge of the socio-technological change right now. It's not all social, only social or technological. It's a combination of the two changes happening at this time. And distributed systems are not the only solution to address the concerns of the geo-privacy or ownership or existing challenges in the spatial data sharing, but they are complementary solution with the centralized systems. The technological movement is facilitating the entire change, and in this transition, however, we need to consider cultural and social aspects as well. And if the users are willing to deal with the complexities that appears there when we start to use distributed approach of the sharing data, both in the technology level and even in the policies and relations that exist there. And if we want to use distributed systems, one of the things that exists there is that we need to reinvent most of the things that already solved in the centralized systems, which slows down our utilization of the distributed systems for the public, smaller communities or communities that really benefit from these systems and these new control that they gain. And also we need to have a kind of as I said, the environment gets more complicated, but the ultimate beneficiary of these systems are individuals that are contributing in spatial data sharing. Future research direction, we need to develop tools, method, and algorithms to handle, share, and query geographical information, depending on the data set that we are having and depending on the type of information that we have. We need to have access control methods that is working on distributed systems. We need to have define standards in different levels, from the object definition that you define your object, your point, and you want to apply, let's say, geo-privacy to that, to the higher level of the sharing communication between networks and those levels. This is and it should be able to get integrated to the existing central entities, central standards. We don't want to be separate from everywhere. It should be able to communicate with the existing central entities, but it needs to have its own standards as well to be able to handle internal connections and processes. We need to have more studies about distributed processing of the spatial data, which I didn't touch that part at all in my work, and I like to look at it, but there wasn't enough time. Maybe I didn't spend on that part. We need to have, for example, developing geo-enabled smart contracts to allow us to use the geographical information and analysis there. We don't necessarily need to have, for example, traditional geocomputation power. We can use type of geocomputational like that, we can use DGGS there, discrete global systems there to address that need. And semantic of the data is important. The knowledge that is being shared on distributed data sharing is different per each node that is sharing those data. Each entity individual will be able to share data. So we need to have kind of approach to address this semantic of the data as well. And social capital of the using these systems for a smaller community, for the community, or a larger scale, we need to have study that area as well, because the complexities that these systems bring might prohibit majority of the users from using that. It should be easy to use, and dealing with the keys, different keys, and encryption of the data, knowing those things doesn't help with the making the technology more accessible for the users. At the end, I want to thank you, the Global Water Future program, which provide the entire funding for my research, and thank you for Decentralized Geospatial Web Working Group and Taylor for having me here and letting me share my finding here. Thank you, everyone.
Perfect. Thank you, Majid. So we've got a couple of minutes to the hour, and I know some people may have to leave then. So I think the best thing to do would be open the floor to any questions. So if you've got any questions directed towards Jimo, Bill, or Micah, feel free to raise your hand for one of those, Majid as well, and we can kind of circle back and ask some more technical questions. I know I've got some questions for you, Majid. So just kind of open it up to any questions. Cool. And if we have no burning questions yet to fire up to discussion, I can kind of ask one. So I'll circle to Majid. I think for the OGC discussion, Micah, I can kind of cut the piece of your recording and also circulate that, and we can have an extended discussion at the beginning of the next meeting. So we'll have some time for that to circle back to you.
So sounds great. And if anybody has any questions, you can send me an email and I can answer them during the next meeting. Happy to do that as well.
Sounds good. Majid, I wanted to ask in terms of the indexing, the kind of first thing that you presented. I was curious, you had used, was it an R tree or a quad tree?
Yeah.
In that?
I
was just curious, what was the consideration for selecting that type of spatial index? Did you kind of consider others, or, looking back in hindsight, is there another kind of spatial indexing structure you're maybe thinking about, or did you find the one and you felt like you nailed it on the head?
So the thing is that for that part of the work, I prefer to use quad tree for the reason of the simplicity of the implementation and the entire structure that exists there. But the main requirement for me was that to have a data structure that is more predictable. If you know, for example, you can guess what is the next indices for children of each node, and you know the boundary of that children. So this allows you to have a kind of being able to guess, okay, what is coming next folder or next structure when we get deeper into that tree structure. That was the main concern that I had, which because that structure between parent and child is a uniform structure 1 to 4, we can easily replace it with more advanced tree structures, like, for example, as I said, at the beginning, I wanted to actually use discrete global systems because they have the ability to, that they have that uniform structure, and they also provide ability to have data aggregation, and they're using the indices, those node indexes. But because of the complexities that they also introduced to the work, I choose to go with the quad tree. But it's definitely, there is room to use more advanced data structure there to address the concept. The only requirement is that it should be able to give us a predictability of the what's going on next in each layer after we get deeper into that tree structure and go forward in each node.
Awesome, thank you. Any other questions?
I have one question. Thank you, Majid, for giving such wonderful talk. I have one question. That did you consider placing the temporal indexing after the quad tree, or did you test with that? Like, is there any performance that you sacrifice by placing the temporal indexing after the quad tree?
That's actually a thing that I tried to. My first actually iteration was that I prioritized the spatial tree first, and then I was using the temporal tree. But because of the structure of the temporal interval tree that I was using, it added more processing to the entire work. So I chose to change it because to improve the performance. Also, the requirement that I had in that case study, which was querying data, crime data in Waterloo region, it was a kind of case study that I was working on. I came up with having the temporal tree at the top, but switching between these two, depending on a structure of temporal and quad tree, it can improve or impact and increase the or decrease the performance of your structure, your queries. So if you, for example, you have a data structure, a spatial data structure that has more nodes at top of the tree, you need to check more nodes to get to the temporal query, which impacts your performance. So it depends on your case study and also what type of tree structure you are using, which impact you have to choose which order is better. But in my case study, interval tree and quad tree, the interval tree at top had a better performance.
Thank you.
Any other questions?
I just wanted to ask if Majid had like a link for their organization. I wanted to kind of look more into this. But yeah, that was my only question.
That's actually, I was actually answering your question in the chat.
Oh, sorry. Okay.
The thing is that I have my a couple of the papers published from my work. I can share them with you, but I'm not part of any organization right now. I'm just recently finished my work, so I'm not part of any organization. But you can find me in LinkedIn, and I will be happy to do more research with you.
There's no other questions. I was going to ask one more kind of general question, which was whether or not, Majid, you're interested in kind of plugging in this work to the bigger ecosystem at all. Like John, who had Hojati, he had mentioned the GeoDIDs they were working on, which was to resolve spatial data sets on chain, and that there could be some kind of path forward for building in a query parameter to that could plug into this type of framework. Is that anything that you've kind of thought about or you're interested in?
Thanks for the question. That's actually a good question that I had because this work I started from 2019. So as I was moving forward with different concept of that, at the time I decided to move forward without considering integration of these models to the other systems. But I guess the part of that entire standardization of the system can be the thing that we embedded some of the concepts like those parameters in the bigger systems and work on that. But to be honest, during my research, I didn't look at that area how I can integrate it with the existing system, because each system has their own APIs and data structure and that they are following. So it's a bit of harder to dig into that and see how that's working, you know.
Perfect, thanks. Hope there's no other final questions or comments. I think we'll go ahead. Oh, we've got one. Yeah, please.
I have a question. Hi, I am glad to be here. Majid, I have a question about DDGS. I was a member of another working group from OGC, from DDGS group, and I noticed that you used discrete global system in your research, and it's interesting for me. Which type of DDGS have you used? If I am not mistaken, it was Uber H3. Am I correct?
Yeah. I used
because as I remember, there are at least two another systems in DDGS system, like Google S2, S2 and RealFix, if I'm not mistaken. So it would be nice to mention that you used Uber H3 because I also like hexagons. I used it in my own research and investigations. Also, I have a more general question about decentralization, all these things. I am a full stack WebJS developer, and now I am working very close with Google Cloud infrastructure. And this main idea of decentralization of spatial data, spatial technologies is very attractive for me. It sounds promising. But I have maybe some funny question, but how to have in this system a single place of truth when we have several data providers in this system of decentralization? How to know this boundary of park is correct and this boundary is not correct, it's mistaken? How to filter these things? I would be happy to know the answer.
Yeah, thank you so much for the great question. So to answer the first part of the question, I use the H3 in my work, but yeah, as you mentioned, there are other RealFix, S2, or there is dGWWG, which Dr. Kevin Sayer is working on, that which provides the hexagon, square, triangle grids, and all of them existed, but H3 were more accessible and they had different libraries for JavaScript that I used. So for the answer, the second part of the question is that I guess for having the single point of truth, in the DS3, my approach was that as the data is being added to the tree structure, we save the latest version of that tree structure on the chain. So we have the latest version always there. But having the validation approach for that, if the data is there is valid or not, I didn't look into that. So that's some part of that. I guess it can be, using centralized consensus that exists there should be able to address it, but the validation of the data itself, it depends on the ranking of the nodes that are contributing there, or how that node is, how valid is that node that is contributing there. I guess that would be one of the approaches that we can take, but that's a kind of, I guess, research area to have a look at it, how we can validate that part of piece of data that is added to the network and which version is the true one. But in my approach, then I consider the latest version as a true and valid one. It was an assumption of my research.
Okay, sorry for answer. Just final suggestion for me: if you have any plans of practical implementation of your idea and to create some maybe simple example of decentralization system, I would like to be a part of it. Just let me know. We have connected in LinkedIn, as I remember.
Yeah, that would be awesome. Thank you. Thank you so much. Yeah.
All right, we're running quite a bit over the hour, so I'm going to go ahead and say we'll wrap for today, and then I'll be in touch. We'll have some details about the next meeting in about 2 months from now. Thanks everyone. Thanks again, Majid, for the presentation, and we'll see you next time.
Thank you, Taylor. Thank you, everyone.
Take care.
Bye.
Yeah, everyone.
Thanks, guys.